Welcome to this video about a very important application of complex numbers in electrical engineering. It is about the calculation of the total impedance, so the total resistance, so to say, in an RLC circuit. So first of all, let me draw the RLC circuit for you. So you see here the resistor and the inductance are in parallel, so resistor R, inductance L, and the capacitance here, they are in series and the capacitance is in parallel. So what is given? First of all, the omega is given, the angular frequency, the resistance R is given, the inductance L and the capacitance C is given, and they are all positive fixed numbers. So this order is important also in the calculation. So you see here RLC circuit is given and also here RLC, and it would be good if you stick to this order. Okay, what is the total impedance of R and L in series, which I call complex impedance Z1. So it's just R plus I omega L. In electrical engineering, you will actually write here a J, that there is no misunderstanding with the current I, but in mathematics, we use I for the imaginary number. You also will learn in electrical engineering why is it I omega L. So Z2, it is 1 divided by I omega C. So this video is not about the content or the domain knowledge of this electrical circuit. It is purely about the computation of the total impedance and how to do this efficiently. So we have to bring Z1 and Z2 in parallel, and you also might learn in EE lectures that the inverse of Z is just the addition of these Z1 and Z2, and you can compute the common denominator. Like that. Okay, so actually this is what we need to compute, but you have to invert it. So we start here. It's a very long computation what's following, and we have to be very careful not to introduce any errors. So in math lectures, you do not have to memorize these formulas. They are given. But from now on, this is what you should be able to do. So Z1 plus Z2 is just a summation. This is just a copying exercise. And in the numerator, you have to multiply. So what is the first step? How to compute this efficiently? And the first step is that you multiply it with I omega C to get rid of these double fractions. No one likes to deal with double fractions. So what does it mean? The numerator here is R plus I omega L. And in the denominator, you have now 1. I would start here with this 1 here. Plus, the next one is here. Probably use the intermediate, this one, the middle term, because it also will be real. Why? Because I times I is I squared, which is minus 1. So this is actually a minus. And now we want the same order as here. So we start with omega squared. Then we need there is no R, then we need the L. which is here, and 1c plus last part. So we multiply this with that one. Sorry, this is what we did now. The resistor with I omega c. So we start with the complex number I omega and then R and C. So same order as given here. Great. This is not what people are satisfied in engineering. So you want real part plus I imaginary part. So you have actually to make the denominator free of the imaginary number I. Hence, we use the method of conjugate complex expansion. So what we're gonna do here is we expand this with the complex conjugate of the denominator, which is 1 minus omega squared LC. And then now we have, instead of this plus here, we have the minus I omega RC. And in order not to change this expression, you have the same in the numerator. Great. And the last step is expand everything. And this is a lot of work. For the denominator, you might remember a trick which I write here on the left side. You have a complex number a times I plus IB times a minus IB. What is that? Open brackets. So we have a squared minus I squared b by the binomial formula, and I squared is minus 1. So you end up with a squared plus b squared. This would be great if you remember this, because you can save a lot of time. So the multiplication with the conjugate is a squared plus b squared. So this is actually the magnitude of the complex number squared at the end. But we don't need this here, so use it. It's 1 minus omega squared LC squared plus, always plus, you don't have to worry about this sign. So it's like a squared real part plus imaginary part squared, what we did here. And in the numerator, you just have to do the multiplication. So we start with R plus I omega L times the 1. This means this is just copying. Then the next is minus omega squared RLC. So what I did here is minus omega squared, this one, times the R. And now you do the same with, what do we need? With the R here. Sorry, not with the R, I want this one, not to forget it. So we have here plus, no, minus, I omega cubed L squared C. So what I did is this one times that one. Okay, I'm running out of colors here, but what remains is R plus I omega L with the last one. So with that, multiplication with R is not so difficult. You just have R squared instead. But the last one is then minus I squared. I squared is plus 1, so plus omega squared R L C. So if you stick at least to the order given from above, you have some structure, and it's a little bit easier, although it's very time consuming to do this calculation. What can you see in addition? That this is canceling out with the last one, so it's a bit easier, and you can read off the real part. Where is the real part? It's this one. So this is the real part, and the imaginary part, I use the yellow one. Imaginary part without the I. So without the I is here. This one divided by the denominator. And don't forget the minuses in the imaginary part. Thank you very much for your attention.